Yes, good evening to all. This is Veeraswamy, working as an assistant professor in the Department of Electronics and Communication Engineering in the Institute of Aeronautical Engineering, Hyderabad. Today, we are going to discuss the topic from the mobile communication system. The topic is a design of antenna system. So, here in the last session, we already discussed that what are the basic parameters required to design an antenna. So today we are going to design the antenna system. So how we are going to design antenna, what are the different types of antenna and what are the parameters we have to consider to design a system, that is the antenna system. What are the parameters required to design a antenna system? So here basically before entering into these topics, these slides are prepared by referring this textbook, that is Mobile Cellular Telecommunication, and the author is William C. Wiley, Tata McGraw-Hill Publishing Company Limited. So the today's topic is the design of antenna system. So the design of antenna system, here we are considering the different types. Already we discussed in the yesterday class, that is different types of antennas we are going to design here, that is omnidirectional antenna as well as a directional antenna. So the design of an omnidirectional antenna system in the worst case. So here in the worst case, the design of an omnidirectional antenna system in the worst case. So the worst case, how we are saying the worst case? Why we are taking the worst case before we are going to design the antenna? So the worst case is at the location where the weakest signal from its own cell site, but strong interference from all the interfering cell sites. That's why we are taking the worst case here. So in the worst case, the mobile unit is at the cell boundary R. Already we know that R is nothing but here the radius of the base station or the radius of the cell site. As well as here the D is nothing but distance from the cell site here, cell site to another cell site. The D plus R, D minus R, already we discussed in the yesterday's class by taking some of the examples of images. So here that the two distances here, the two distances we are taking at the D minus R, that is D minus R and the 2D, the D plus R. That is already we know that the D is nothing but a distance of the cell site. So here two distances of D minus R, two distances of D and two distances of D plus R we are going to consider in today's in this topic. So here in the design of omnidirectional antenna worst case, in the value of Q here. So already we know that what is the Q here? The Q is nothing but here co-channel interference reduction factor is nothing but here Q here. So how can we calculate the Q value? The Q is nothing but it is depending upon D by R here. So already we know here what is D and what is R. So then the D is nothing but a minimum distance between the cell site and the radius is nothing but the cell cover, the area zone or the zone is covered by the cell site is called as R. So then we are calculating the co-channel interference reduction factor. The Q is equal to R, and already we know that when the Q value is very high, then the co-channel interference is very less here. When the value of Q value is very less, then the high interference will be occurring in the co-channels, right? So already we know that. But here what we are doing in the worst case here, we are taking the value, the Q value is equal to 4.6 here for the 7 cell cluster. That is nothing but here K is equal to 7 cell pattern we are taking here. So the antenna pattern also we have to consider here. So the antenna pattern here is the number of cells are 7 here. So the value of Q is equal to 4.6 is valid for a normal interference, then the K value is equal to 7 cell pattern. So the worst case is at the location where the weakest signal from its own base station, but strong interference from all the interfering cell sites. Then the worst case R we are taking, already we discussed the D minus R, the two distances are, that is D, two distances of D plus R and two distances of D minus R. So to calculate here, the following of the for mobile propagation rule, according to the mobile radio propagation, that is we have to obtain the C value here and the I value. C is nothing but the carrier power and I is nothing but here interference. So the C is indirectly proportional to the R by 1 power 4. Already we discussed that the C is indirectly proportional to R power 4 and the interference is also the interference I is indirectly proportional to 1 by D power 4. That is here The C is nothing but received power. It is based on the radius of the cell site, and as well as the interference is also depending upon the distance from the minimal distance from the cell site to another cell site are co-channels. So from these two, by taking these two parameters, that is the C value and I value, the C is nothing but carrier power, that is received carrier power, and I is nothing but interference here. So by considering these two parameters, we have to calculate the carrier to interference ratio, that is carrier to interference ratio, that is given as here C by I. So here the C is nothing but received carrier power, and I is already we discussed that. The I is nothing but here interference at the co-channels are interference in the adjacent cells. So that is the C by I is given as R power minus 4 upon 2 of D minus R power minus 4 plus 2 of D power of R minus 2 of D power minus 4 plus 2 of D plus R whole power minus 4. So this is in terms of D and R, distance and radius of the cell site. But if they will give the Q factor value, that is co-channel interference reduction factor value, if they will give Q value, so then how to calculate the C by I? So see here, by taking the same parameters here, the 1 by 2 of Q minus 4, just we are taking here the R value is equal to 1 and the here D is equal to Q. We are taking the value, just substituting here. I am repeating again. In place of R is equal to, we are taking as 1, and in place of D is equal to, we are taking as Q. Just substituting in this equation. We are just substituting these values in this equation. Then we are getting the carrier to interference ratio, that is 1 by 2 of Q minus 1 power minus 4 plus 2 of Q power minus 4 plus 2 of Q plus whole power minus 4. So this is the equation to calculate the carrier to interference ratio. Clear? Next. So here, just now we discussed the D and what is D minus R and D plus R here. Right? So two distances of the adjacent cells, that is D, D plus R and D minus R. That is in the worst case we are taking the co-channel interference in the worst case. See, this is the best example. The image, this is the image represents the co-channel interference in the worst case antenna designs. Next. So see here. This is the D minus R and this is D plus R. This is also D plus R. So how can we identify what is D and what is D plus R and what is D minus R? If here, this is the base station here, from base station to this base station here, at the boundary of the cell 2, the base station distance is given as D minus R here, and this is the minimal distance, that is D minimal distance here, and the radius is here less. That's why we are taking as D plus R. And here is the radius, the boundary to the radius of this cell set is very long. That's why we are taking as D minus R. So this is the way to identify the what is D minus R, what is D plus R. Right? Next. So just now we discussed that when we are considering the cell site, that is K is equal to 7 parameters we are taking, right? So when K is equal to 7 and we are taking, assuming the value Q factor, that is co-channel interference reduction factor Q is equal to given as 4.6. So then, where the Q.6, that is Q is equal to 4.6 is derived from the normal case substituting Q is equal to 4.6 value into the above equation. So see, this is the equation, right? So here, I will write once again here, the equation I will write here. Right, I will write here the equation here, that C by I is equal R power minus 4 by 2 of D minus R power whole power minus 4 plus 2 of D power minus 4 plus 2 of D plus R power minus 4. Right? Then from this equation, just we are substituting R is equal to 1 and D is equal to Q. Then what we are getting? Then C by I is equal 1 by 2 of Q minus 1 power minus 4 plus 2 of Q power minus 4 plus 2 of Q plus 1 power minus 4. These are the. So just substitute here Q is equal to 4.6 in this equation. Just substitute Q is equal to 4.6 here. Then we are getting the C by I value is equal to 54 here. That is in terms of decibel, that is 17 decibels value we are getting. Then see, which is lower than 18 dB. So to the conservative, we may use the shortest distance D minus R for the 6 interference at the worst case. Then we have this equation to calculate, that is r power minus 4 by 6 of d of r minus d minus r power minus 4. Then just again substitute r is equal to 1 and d is equal to q. Then again we are getting the 28 here. The 28 is nothing but here, that is less than 18, that is 14 dB. So when the 7 cell we are considering, that is we are getting the C by I value is 54. When 6 cells we are taking, then we are getting the C by I value is 28, that is in terms of dB, that is 14.47 dB. So in reality, the perfect locations and rolling nature of the terrain configuration, the CI by ratio, in the worst case, we are getting 7, right? So when we are getting 7 dB, so we are getting 7 dB at the, when taking we are k is equal to 7 and q is equal to 4.6, then we are getting the worst case, that is 17 could be, and there could be 14 dB is lower. Such an instant case easily occur in a heavy traffic. So when the heavy traffic is in situation, therefore the system must be designed around the C by I of the worst case. So in that case, the co-channel interference reduction factor, that is q is equal to 4.6, is insufficient to design the antenna and insufficient to design the base station. So therefore, in an unidirectional cell system, we are taking k is equal to 9 or k is equal to 12. That is, already we know that how we are taking k is equal to 9, k is equal to 12. The cluster size, always the cluster size is 7, 9 and 12 we are taking parameter, that is our 4, 7, 9, 12. So here we are considering the values of q are here, d by r is nothing but root 3k and 5.2 for 9 cells and 6 is equal to for 12 cells. So by substituting these values in the C by I value, that is C by I equation, then we are getting here 9 dB. When the 9 k is equal to 9, we have to substitute q value as 5.2, then we are getting 19 dB of C by I value, that is carrier to interference ratio. And again, when we are taking the cluster size is 12 and we are substituting q value as the 6. So when the cluster size is 12, then q value is 6, right? So then we are substituting the 6 value in the equation of C by I, the carrier to interference ratio, that is, then we are getting the 22 dB. So the design of the directional antenna, just now we have discussed the omnidirectional antenna. So now it is the design of a directional antenna system. So when the call traffic begins in the increase, we need to use the frequency spectrum efficiently, right? So when the traffic is increasing, automatically we have to increase the frequency. That is nothing but here the frequency spectrum we have to efficiently we have to utilize and avoid the increasing the number of cells, right? So the number of frequency channel assigned in a cell must become smaller and efficiency of applying the frequency release schemes decreases. So I am repeating once again this topic here, this slide. When the call traffic begins increases, it means when the number of customers are increasing. So then we need to increase the frequency spectrum efficiency. We have to increase the number of cells to avoid the number of call drops. So at the same time, the number of frequency channels assigned in the cell must become smaller. When the customers are increasing or the mobile units are increasing, then automatically the efficiency will be decreased, right? So then we have to apply the frequency release channel, that is frequency release automatically decreasing. So this is the one is the defect here. So the co-channel interference, already we discussed that the cell is using same frequency. The adjacent cells are using same frequencies, that is called as the co-channels, and that is interference. When the interference will occurs in between the co-channels or adjacent channel, that is called as the co-channel interference. So unlike the thermal noise is nothing but here when the mobile unit is moving. When the mobile unit is moving, the noise is added to the message signal. That is called as the thermal noise here. So to overcome by increasing the signal to noise ratio, the co-channel interface cannot be combined. That is combated by simply increasing the carrier power of the transmitter. Next, the co-channel interference can be reduced by using directional antenna. Then how we can reduce the co-channel interference by using this directional antenna? This means that each cell is divided into 3 or 6 sectors, right? So here already we discussed the sectoring topic as well as cell splitting. So by using the directional antenna, we can reduce the co-channel interference. So this means that each cell is dividing into 3 or 6 sectors that uses 3 or 6 directional antenna base stations, right? So already we discussed that here the cell splitting. the cell splitting, right? So cell splitting is nothing but here a large base station or the high transmitter power device is splitting into small, the are nothing but the lower transmitter power, or a large cell is dividing into small cells in nothing but micro cells, and each micro cell has its own base station. So each base station, each micro cell has its own base station, right? So that's why here the sectoring is nothing but here the each base station have its directional antenna base station. That is the concept here, right? So directional antenna here is nothing but the 6 sector or 3 sectors we are doing, right? So that 3 or 6 sector, the directional antennas at the base station, and the each sector is assigned the set of frequencies. Here, what we are doing here, that we are using the directional antenna for each sector, we are assigning set of frequency channels. Then the interference between co-channels will be decreases automatically, because of when the increasing, the customers are increasing or the cells are increasing or the calls or the traffic is increasing, then we are doing sectoring method, that is 6 or 3 sectoring, right? So these 3 or 6 directional antenna base stations we are establishing automatically. So when we are increasing the base station, when the base station we are increasing or a sectoring, we are doing the sectoring, for each sector we are assigning 10 to 50 frequency channels. So then automatically the interference will be decreases between those co-channels. Then automatically the co-channel interference will be decreased. The 3 sector case, just now we discussed the 3 or 6 sectors we are doing, we are taking examples here. So in a 3 sector case, the interference is effective in only in one direction, because of the front to back ratio of cell site directional antenna is at least 10 dB or more in mobile radio environment. Already we discussed what is mobile radio environment, how the signals are traveling in the mobile radio environment. So here in 3 sector case, the effective only in one directional, that is front to back ratio. So that is the front to back cell side directional antenna at least 10 dB or more than in the 10 dB of the signal will be propagated, radiate in the mobile radio environment. So in the worst case, the co-channel interference in the directional antenna sector in the interference occurs may be calculated here. So how to calculate? And they see here, the value of C by I can be obtained the following expression. Already we know C by I is equal R power minus 4 by 2 of D minus R whole power 4 plus 2 of D power minus R, D power minus 4 plus 2 of D plus R power of minus 4. But here we are doing sectoring. Then automatically the equation C by I is equal to R power minus 4 by D plus 0.7 R power minus 4 plus D power minus 4. In terms of reduction factor, that is R power minus 4 by Q plus 0.7 power minus 4 plus Q power minus 4. So this is the equation to calculate in the 3 sectors channels. And the see example here, this is the image, 3 sectoring, that is the interference cell in the 7 cell system here, 2 tiers. So 1 tier is nothing but here 3 sectoring. But here we are taking the interference cell between the 7 cell system. So see what are the 7 cells here? Here 1, 2, 3, 4, 5, 6, and here it is 7. See, right? 1, 2, 3, 4, 5, 6, and 7 sectoring. This is the 2 tiers. Then here 120 degree channels are there, 60 degree. So then what is 120? What is 60? 60 degrees, 60 degree directional antenna, and here it is 120 degree antenna, and here it is omnidirectional. So we see, observe here. See the dotted lines here, given here. This one is here. So this part, this is 60 degree of directional antenna. Then see this one. This part is nothing but 120 degree of directional antenna. This is 60 degree. And see here, both sides. Here, both sides. So this is nothing but here omnidirectional antenna. So here omnidirectional antenna, but we can the signal will be radiates in the all directions. That type of antenna is called as the omnidirectional antenna, right? Next. So the antenna parameters and their effects. So basically here, when we are designing antenna, we have to consider some parameters and their effects also, right? So the lowering antenna height, the antenna height. So lowering the antenna height does not always reduce the co-channel interference. When we are decreasing the height of the antenna here, that means the lowering the antenna height is nothing but when we are decreasing the height of the antenna, that is the not method to reduce the interference, right? So the lowering antenna height does not always reduce the co-channel interference. In some circumstances, such as a fairly flat ground or in a valley situation, the lowering the antenna height will be very effective for reducing the co-channel interference as well as the adjacent channel interference also. So, however, there are three cases for lowering the antenna height may not be effectively reduce the co-channel interference, right? This is the lowering. So, the parameter here we have to consider effective. The parameter is when we are reducing the height of the antenna, that is the not method, exact method to reduce the co-channel interference, right? The next one is the height of the hill at the high spot. So, the effective antenna height rather than the actual height is always considered the system design. Therefore, the effective antenna height varies according to the location of the mobile unit when the antenna site is on the build. The next, see here. So, here the two images, image A and image B are there. This is the flat surface. Flat surface. Here, the lowering the antenna on high hill. This is high hill, and this is the in a valley. So see here, this is the height of the antenna. This is nothing but height of the base station, height of the antenna, and this is the mobile unit, and here also it is a mobile unit. So this is the best example. See here. So just now we discussed the parameter that is effects of the antenna. Here it is. One is lowering the height of the antenna, and the second one is on a high hill or a high spot. So this is the high hill, and this is the mobile unit, and the base station height is this one. So this is the propagation signal. Right? Clear. Next. So if we reduce the actual antenna height, just now we discussed the effect of the that parameters, antenna parameter that will affect, that is to reduce the height of the antenna, the lowering the height of the antenna. So if we reduce the actual height of the antenna, that is to 0.5 h1, the effective antenna height becomes 0.5 h plus h. To reduce the gain resulting from the high reduction is, so here G is nothing but here the gain reduction. So the gain reduction is calculated as 20 log base 10 is nothing but 0.5 h1 h plus capital H by h1 plus capital H. So just now we discussed that in terms of this is the gain reduction factor G is equal to 20 log base 10 of 1 minus 0.5 h1. We are taking H is common here by h1 plus h. Right? Yes. If h1 from the equation, the before previous equation, this h1 is greater than less than h. This one, the h1. The h1 is very less than the gain the height of the antenna. Then we are getting the value that is 20 log 1, that is 0 dB. Clear? So the above equation, from the above equation, what is the above equation here? 20 log S10 of 1 minus 0.5 h1 by h1 plus capital H. Right. From this equation, when h1 is less than h, then we are getting 0 dB. This simply proves the lowering the antenna height on a kill does not reduce the received power at the cell site or at the mobile unit. Then the parameter again affecting in a valley. Just now we discussed that in a hilly or in a valley, and lowering the antenna, but here in a hilly valley, that the effective antenna height is seen from the mobile unit. Just now here see the in the figure. I will show the figure. This is the figure, right? I will show. Right. So here He1 which is less than the actual antenna. Just now we discussed that H1 is less than the actual height of the antenna. Then we have to consider then the new effective antenna height is given as He of 1. Effective antenna 1 is given as 1 by 2 of H1 is minus of H1 minus 2 by 3 of H1 is equal to given as 1 by 6 H1. This is the When the antenna is in a valley and mobile unit is in the surface, at surface, then we have to calculate the new effective antenna height. We have to design the antenna by having this, that is 1 by 6 of h1. Right. So here the diversities, the space diversity here, the basically different types of diversities are available in here in the designing of the antenna. That is the one is space diversity, frequency diversity, and time diversity. Different diversity considerations are available. So what is space diversity? The space diversity is also known as in the antenna diversity. It is the one of the most popular form of diversity used in wireless systems. When we are designing antenna system, we have to consider the diversity techniques also, right? So the space diversity consideration, this space diversity consideration also known as the antenna diversity. So this antenna diversity most popular in the diversity used in the wireless system. The concept antenna space diversity is also used in the base station design. So the space diversity can thus be used in either the mobile unit base station or in the mobile unit or base station or in the both. So see the figure here. So here these are the antennas and these are the variable gains here, and the switching logic device or demodulators are available here to are getting the output. So the generalized block diagram, the space diversity. So what we are doing in the space diversity? So all the antennas are connected to the variable gain here only, not in a fixed gain. So all the antennas we are connecting. When we are designing an antenna, we have to consider space diversity parameters also. So the space diversity parameter here, the antenna is connected to the variable gain only. Then the variable gain is connected to demodulator circuit. The demodulator gives us the output of from the antenna gain is the output we are getting at the demodulator circuit. The next one is the polarization diversity. At the base station, space diversity is considerably less practical than mobile because the narrow angle of incident fields require large number of spacings. That's why the circular and the linear polarized antennas we have used the characterize the multipath inside the buildings. So the space diversity can be either the mobile or the base station or both. So see here the figure I given here. Frequency diversity from this figure only. Next, the frequency diversity. Just now we discussed the basically 4 types of diversity. That is space diversity, frequency diversity, polarization diversity, and time diversity. So the frequency diversity transmit the information one or more than the carrier frequency. The frequency diversity transmit information on more than one carrier frequency. So the rationale behind this technique, that is the frequency is separated by more than one coherence bandwidth of the channel that will not experience the same fades. Theoretically, if the channels are uncorrelated, the probability simultaneously fading will affect the product of the individual fading probabilities. The next one is time diversity. The time diversity repeatedly transmit information at the time spacings that exceed the coherence time of the channel, so that the multiple repetitions of the signal will be received with independent fading conditions. So thereby providing for diversity. One modern implementation of the time diversity involves the use of the reg receiver spectrum that on the code division multiple access, where the multipath channel provide redundancy in the transmitted messages. So here the time diversity is nothing but here the time diversity repeatedly transmit the information on the spacing that exceed the coherent channel time. Then the modern implementation of the time diversity involves the use of a Iraqi receiver for the spectrum that on the code division multiple access, where the multipath channel provides the redundancy in the transmitted messages. So these are the today's topic. We will discuss the next topic with the new topic in the next session with the new topics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.